All right, well, welcome everyone. It's good to be back with you. Even though it's Tuesday, it sort of feels like the beginning of a week because we didn't get a chance to be all together as a group yesterday. And so let's dive into our new material. So when last we saw our intrepid heroes, we were introducing this new concept of a triple integral. So triple integral is it's easiest to think about as a means of calculating a volume, but it's much more powerful than that. It's a method of integrating across a three-dimensional space. And common applications are going to be to find volume or mass or moments or things along those lines. But the concept exists in the abstract as well, separate from applications. And remember that distinction that a triple integral is a quantity, but there isn't any built-in method for actually evaluating it or finding it. And so we're going to always be turning those triple integrals into iterated integrals, which we can actually evaluate. An iterated integral being one that has the limits of integration. So when we were working on triple integrals last week, we were working exclusively within rectangular coordinates or Cartesian coordinates. Just like we had polar coordinates and rectangular coordinates in to work with double integrals, here we have multiple coordinate systems when working with triple integrals. And so today we're going to introduce two new coordinate systems, cylindrical coordinates and spherical coordinates. And those are going to give us two other coordinate systems and kind of some accompanying power. They're going to be particularly helpful when we integrate certain types of integrands or across certain types of regions. So without further ado, let's dive into our notes. So our objective is to understand spherical and cylindrical coordinates. We're going to play with triple integrals in cylindrical coordinates and triple integrals in spherical coordinates. At the outset of the notes, we have kind of some verbiage kind of explaining it in words. But I want to focus in on first on this application. So one of the obvious applications of spherical coordinates is to this idea of navigation with longitude and latitude. And so you can think about the longitude is telling you how far north-south you are. The latitude is telling you how far east-west you are. And in some ways, those are going to be analogous to spherical coordinates. It's not perfect because we're going to have a third spherical coordinate, which is going to be how close to the center of the object we are. And in this case, most of the surface of the Earth is kind of a fixed distance from the center of the Earth. The coordinates themselves are interesting in terms of the letters chosen. I'm going to move forward to and manipulate in a moment, but let's just focus here for a second. So in rectangular coordinates, we have x, y, and z. Cylindrical coordinates is going to parallel the polar coordinates that you worked with before. So this is the same r and the same theta that you had in polar coordinates, and it's the same z. It's the same z here and here.
Steve?
Yep, go ahead.
Will our theta always be on the XY plane?
We can, good question. So we can always construct our system so that the r and the theta are in reference to the XY plane. So if the question was, if the cylinder was coming towards us, we could just reorient and relabel the axes if we needed to.
Okay.
So in spherical coordinates, we now have three variables: rho, theta, and phi. So this is rho as in row, row, row your boat. And this is phi as in phi, phi, fo, fum. So the rho is taking the place of our r, and basically it's the distance from the origin out to the point. The theta is the same theta that you're used to, And phi is interesting. This is the one you got to be careful with. Phi is the angle from the positive z-axis down to that kind of radius. So it's from the positive z-axis. And so if you can look at looking at the camera again, everything's mirrored for me, pardon me. So if you think about, this is the positive z-axis. So to find phi, we're going to ask, what's the angle as we rotate down? So this would be phi equals 0, maybe phi equals pi over 4, phi equals pi over 2 or 90 degrees, phi equals 3 pi over 4 or 135 degrees, phi equals pi or 180 degrees. And then it stops. So phi only ranges between 0 and pi. And again, 0 is straight up. Pi over 4, 45 degrees. Pi over 2, 90 degrees. 3 pi over 4, 135 degrees. Pi, 180 degrees. So it's positive, 0 is straight up. 90 degrees is horizontal. Pi is straight down. It's not hard, but it's just sort of a new orientation. And so it's worth spending a moment there. You can see that, you can see the those limits happening for our phi right here. Phi is between 0 and pi. I want to pull out an animation of this, but are there any questions before I switch over to an animation?
Sure. And is this like unlike cylindrical where we cannot change our coordinate system because of this z?
Can you ask that again?
When I asked with cylindrical coordinates, I asked if we're always doing theta with respect to the xy plane.
Mm-hmm.
And then we said that we could relabel our axes.
Mm-hmm.
So with the spherical, would we not be able to relabel our axes? But if we do, we just got to make sure that our z is always pointing up, quote unquote.
Got it. I understand the question. So at the beginning of most application questions, you have the opportunity to do what I call coordinatize. Let me type that in there. To coordinatize, that is, if I ask you a question about spheres, there's no inherent X, Y, or Z in that sphere. If I ask you a question about boats, there's no inherent, up, down, left, right there. And so the first thing you do when you draw that picture is you sketch axes, and you get the choice of how you label those axes. So if you're on a boat, as a landlubber, I call it, forward, back, left, right, up, and down. But if I'm a Navy guy, maybe I call it port and starboard and fore and aft, and who knows what they call up and down. Like, you can think about those as different names for various coordinate systems. So since you get the choice of coordinatizing, you get the choice of where to put your origin and where to put those axes. And so the beautiful part about mathematics is you always have freedom. It might cost you if you choose something strange, but nevertheless, you have the freedom to choose whichever system kind of works best for you, whether you're in rectangular coordinates, cylindrical coordinates, or spherical coordinates. Did that answer your question?
Yes, thanks.
Cool. Thank you. All right, let's look at the first animation. Okay, so I want to talk about cylindrical coordinates for a moment. Come on. So if we're looking at the point P up here, r, theta, and z, you can think about r. Oh, r is the radius, like the distance that our point is from the positive z-axis. or you could think about it, it's kind of that red, the length of that red line, right? So here's that red line, and so r is that length. Theta, this is your friend that you know from before. It's going to be the angle swept out. Notice it's still the angle swept out from the positive x-axis, just like before. It's just now we're in 3 dimensions, so the axis looks a little funny. And then z is just like you'd expect, it's the vertical distance. So r, the angle swept out from the positive x-axis. Sorry, r is the distance from the positive z-axis, or from the z-axis. Theta is the angle swept out from the positive x-axis. And z is the height above the xy plane, or below the xy plane. So that should make sense. So a simple question that kind of comes with this is that what does it look like if you hold a variable constant? So for example, if you're in rectangular coordinates and we say x equals x naught, or think maybe x equals 2, x equals 2 or x equals x naught would be this plane, like this vertical plane parallel to the YZ plane, perpendicular to the x-axis. Y equals a constant would be a plane parallel to the XZ plane. And Z equals a constant would be a plane parallel to the XY plane. That should be old and familiar. But what happens if we apply the same thing in cylindrical coordinates? So for example, what happens if we let our r be constant? So if we let our r be constant, we're going to get a cylinder. So notice the radius of the cylinder is that same red length r, and then so we get a circle, but then it has infinite height. It can go up infinitely, it can go down infinitely. Okay. So if r is a constant, you get a cylinder. How about if theta is a constant? What are we going to get?
A plane.
We're going to get a plane, good. And it's an interesting plane in that this particular plane starts at the axis and it only goes out one direction. So notice that it's not continuing back in this region. It's just moving in the direction of positive r's. Okay. And it's a plane that's rotating rather than parallel to an axis. Okay with theta being a constant?
Wait, what if we change the value of z with theta constant?
With theta being constant and you change the value of z, all you're doing is you're changing which height we are on that plane. So in some ways, maybe it would be easiest to think about it like this. This would be theta is a constant. There's no r's, there's no z's. Or maybe it's all positive r's, all z's might be an easier way, more accurate way of saying it. Did that answer your question, Enrique?
Yes, thank you.
Okay. What about if z is a constant? So if z is a constant, you'll end up with this plane, horizontal plane, at whatever height we choose. Good. So questions about cylindrical coordinates and or what it looks like if r, theta, or z are constant? Very good. Well, since that was so much fun, let's do the same thing, but with cylindrical coordinates. All right. So like we were talking about, in cylindrical coordinates, there are 3 letters. So we've got row, as in row, row, row your boat. We've got
Spherical?
Sorry, thank you. In spherical coordinates, I appreciate that. In spherical coordinates, we have 3 variables. Row, as in row, row, row your boat. Phi, as in fee, fi, fo, fum. And theta. One thing might jump out to you about this versus the notes. Anybody see what's going on?
They're the phi and the theta are in opposite places.
Yeah, the order is swapped. And so I think what that's a reflection on is that there isn't a standard order for which order you put the phis and the thetas. And the handout reflecting what is in Jimmy Stewart calculus, you had theta, then phi, but in here, reflective of what's in the Briggs calculus, you have the opposite order. And so that leads to a good pro tip. So if you're going to list a coordinate pair, sometimes it pays, or in this case, a coordinate triple, it pays to write out what that order is. So here we might say it's 2, pi over 6 and pi, something like that. We're like, well, what does this represent? Is this the theta or is this the phi? Oh, it's the phi because we can see the order that's given. And so by listing off the order on this side of the coordinate triple, we will make it clear what it is that we're listing when we talk about a coordinate there. Not necessary, but sometimes can help with clarity. Does that make sense to people? Very good. So we have this point. So our point is rho phi theta, and rho is the distance that we are from the origin. My animation won't allow it, but if we had a negative rho, it would puncture through the other direction, just like we had in polar coordinates. So rho it's a radius, but it's bigger than a radius. Like your old r is the one that's down here on the xy plane. Your new rho is actually in 3 dimensions. Okay. Your phi, just like we talked about before, starts at 0, comes down to pi over 2, and then continues on to pi. So phi starts up at the positive axis and works its way down. And theta is the same as before, sweeping out from the positive x-axis. I'd like to put you, so we just talked about cylindrical coordinates, spherical coordinates, and some of those basic shapes in cylindrical coordinates. I'd like to put you in breakout groups for a couple minutes and see whether you're okay with what the various variables represent before we go any farther. So let's take a couple minutes and go into some breakout rooms. Cynthia, do you have a question? if the headphones music.
Which headphones are you using?
I was using Mom's wireless ones. They go
Oh,
beep.
that means they're dying.
Okay. How much life do they have?
I don't know.
Okay.
Wow, that mic is really powerful.
Is it working?
Yeah, I can hear Dustin. I could hear Dustin talking just now. On it.
Oh,
Through Zoom.
nice. We might need to change it to the more pointed and less omnidirectional. Thanks, Guy. Stacey, could you try talking? I just switched headsets. Can you just tell me whether these are working?
What's up?
Thank you. Not quite as nice sounding or as comfortable, but still working.
Did you plug Mom's headphones in?
I didn't. I don't have a charger in here, but
Okay, just probably make sure you plug them in when you finish class or whatever.
that was my plan. Mauricio, Timothy, Melissa, how's it going? Thoughts on cylindrical or spherical coordinates?
They're pretty straightforward.
Yeah. It's not the understanding what the coordinates are that's tough, it's the using them.
Hello.
Hello. Welcome back. Hair's looking good, Devin. So let's complete this thought on spherical coordinates and make sure that we're comfortable with what happens if the various variables are constant. So if our rho is constant, then it might shock you to realize we have a sphere. We're in spherical coordinates. Spheres are really easy to describe. If our theta is constant, we again have that half plane. So, sorry, yeah, I said that right. Go ahead, Enrique.
Oh, I was saying that plane is through Z, not parallel to anything.
Right, it's through the z-axis. It's not parallel to any of to either the xy plane, yz, or something like that. The most interesting one in spherical coordinates is what happens when phi is constant. And you'll notice that when phi is constant, you have a cone.
So in the case of theta being constant, it's a plane that's parallel with the z?
Right, so it's right along the z-axis.
Okay.
Yeah, and it doesn't include, it's only going one direction, right? It's just half the plane. It's not allowing for the negative values, which is kind of a reference to what Robert was saying earlier. Good question. So again, if you have phi being a constant, you have a cone. So notice that describing ice cream cones is pretty easy in this system because phi equals a constant gives you the cone, not theta. Rho being constant gives you a dome on the top. And so we can create an ice cream cone just with a constant rho, and a constant phi, which is like a good tasting thing when you can create ice cream quickly.
That was chuckle worthy.
Yeah, thank you, I appreciate that. All right, so those are the coordinate systems. The question is, what do we do with them? And so we're going to start by just doing some algebraic manipulations. And in order to do that, we're going to need some formulas. So the formulas that we're going to want are going to be the ones that allow us to convert between coordinate systems. So if we're working with cylindrical coordinates, then we get x is equal to r cosine theta, same as polar. Y is equal to r sine theta, same as polar. Z equals z. So you need to memorize these formulas for cylindrical coordinates, but the reality is you already have them memorized. So that's not very exciting. The more exciting thing is in cylindrical coordinates, where you have these uglier looking formulas where x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. And at first glance, that looks kind of intimidating, but I want to point you to how it looks in color. So notice your x value is like a rho cosine phi, and your y is a rho sine phi. That should remind you of
We're
straight
only
up.
seeing you.
Are you showing something on the screen?
Oh yeah, it looks really good on my side, but I didn't share it with you. Thank you for letting me know. Let me go back. Now can you see it?
Yeah.
Take two. Let's try this again. X equals r cosine theta. This is just like in polar. Y equals r sine theta, just like in polar. And z equals z. This is what you need to memorize for cylindrical coordinates, but the reality is there isn't anything new to memorize because this is the same stuff you had in polar. You just have to tack on the z coordinate. So cylindrical formulas are pretty easy. Keep going. Okay. Spherical coordinates are a little bit more interesting. Notice x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. Z is equal to rho cosine phi. That looks a little scary and intimidating. How do you keep track of what's a phi and what's a theta and like what's where? And so what I would like to point out is x is equal to rho cosine theta. Y is equal to rho sine theta. And those are direct parallels to what you had in polar coordinates and cylindrical coordinates. And then your z is equal to rho cosine phi. And it's cosine phi because the z coordinate here is adjacent. This z right here is adjacent to the angle phi. So here's z, it's adjacent to phi, so you end up with a cosine theta. And your x and y, if you will, your x and y are going to be related to this distance, which is opposite phi, and so you're going to have a sine phi. So if you try to memorize for me, when I was a student in Calc 4 way back in the day, trying to memorize these, it was hard to keep track of. But in retrospect, I realized that the formulas actually can make sense to us because the yellow stuff is the same as it was in cylindrical and in polar, and the blue stuff is just simply related to this nice little triangle with the z coordinate being adjacent, tying to cosine, the purple stuff related to x and y being opposite, and so relating to sine. And of course, whereas in polar coordinates and cylindrical coordinates, you had x squared plus y squared equals r squared, here you have the formula for a sphere, or x squared plus y squared plus z squared equals rho squared. Questions about those formulas?
Dusty, in spherical coordinates, each of these angles has a specific name. I know one was transverse. What was the other one?
Ooh, I don't know the answer to that. That's a good question. Let me get back to you on that one as well.
I just remember back when I took 153, that came up on an exam and I got super frustrated because nobody covered it.
I know that it's not my style to ask those kinds of vocab questions, but sometimes I don't even know that I'm asking a vocab question, and I am. So I'll see if I can get back to you on that one and probably post an answer on Slack.
Thank you.
No problem. Okay, so let's see if we can do some algebra and kind of apply these formulas. All right, so this first formula or first equation is written in written in rectangular coordinates, and we want to re-express it in cylindrical coordinates. And we can get some idea that it's going into cylindrical versus polar because there's a z hidden here. So sometimes it doesn't pay to overthink. So x squared plus y squared can be rewritten as r squared. Our x is r cosine theta, and our y is r sine theta. And so we have a nice formula. Now we're in cylindrical coordinates. And we're done. Later on, we're going to use this type of thing when we want to set up integrals and we're converting between coordinate systems. But at this stage, all we're doing is we're manipulating the formulas. So converting from rectangular to cylindrical is not too shabby. We could go, oh, questions about that? Very good. We could go the other direction. And so here at first glance, you might say, boy, that looks like it's a polar formula. There's no z's involved, but perhaps we could just say this thing lives in 3D. And so we want to write in Cartesian or rectangular coordinates. So if we're going to do that, we can take our cosine theta and we can rewrite it as x over r. Multiplying both sides by r, we get r squared equals 4x. R squared equals 4x. R squared can be rewritten as x squared plus y squared. Moving everything to one side, we have x squared minus 4x plus y squared equals 0. And we could complete the square. What do we need to add in here to make a perfect square?
2.
4.
4, thank you. So add 4 to both sides. So x minus 2 quantity squared plus y squared equals 4. And at first glance, you might look at this and say, wow, that looks like it's a circle, right? It's a circle centered at 2, 0. But we now are so much smarter than that because we remember we're in 3D. And so we recognize that what we've actually got is a cylinder. And the center of that cylinder is parallel to the z-axis. Let me see if I can. So here's the z-axis. Here's our y-axis, x-axis. Here's 2. And so the center of the cylinder is at this line, at this vertical line when x equals 2 and y equals 0. And the reason we know it's a cylinder is because of the context of the question, not because there was anything in the formula that tells us it's a cylinder versus a circle. Questions about that? Okay. Very good.
Oh, actually, on a test, would you want us to, complete the square with the equation to get full credit, or would you not mind us just leaving it unsimplified like that?
Leaving it like here?
Yeah.
I think it sort of depends on the question, but probably the easiest answer is that we're just manipulating things at this point. So probably your assessment questions will all be applications of this stuff. And so you would be doing this work maybe as a way of getting the picture that you needed in order to set up your integral. This wouldn't be the question on the assessment itself. Does that make sense?
Yeah, that's what I wanted to hear.
Very good. Very good. Let's do one more example, but this time let's convert to spherical coordinates. So this is example 6, and we're going to start in rectangular, and I want to go to spherical coordinates. Okay. So we need to replace each of these variables using the formulas that were given. So z becomes, why don't you give me those formulas, because you probably don't remember these quite as well.
What are you asking for?
What does z get replaced by in going to spherical coordinates?
Rho,
Rho,
cosine,
cosine theta.
Rho cosine phi. Good. Okay, and then our x is going to be replaced by
P sine
Sine
phi.
phi cosine theta.
cosine theta. We're going to square all that. So this is our x plus rho, just following along, sine phi sine theta squared. Very good. And now we hope things simplify. So let's see what we get here. So we get rho cosine phi equals rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Looks like there's a common factor of cosine, or sorry, not cosine, of rho throughout. So that's nice. And then on the right side, we have a common factor of rho sine phi. Rho sine phi times cosine squared theta plus sine squared theta. Good news.
Isn't it sine square phi?
I lost the square. That's what happened.
Oh, yeah.
Magic.
Yeah.
Thank you. Thanks, Jay. So square there. Cosine squared plus sine squared. Happy one. So we have cosine phi equals rho sine squared phi. And then just like before, if we were in rectangular, we might solve for z. If we were in polar, we might solve for r. Here we can solve for rho. So we get rho equals cosine phi over sine squared phi. Of course, we could do lots of trig identities on this and rewrite it in various other ways if we so chose. But the original question was to take this equation of this paraboloid and rewrite it in spherical coordinates. And sure enough, we've been able to write it in spherical coordinates. Notice there's one variable that doesn't appear. Which variable?
Theta.
Theta. Does it make sense intuitively that there would be no theta in the solution?
Yes.
And please explain.
Well, because we're dealing with, oh goodness. We're dealing with something that is defined 360 degrees about the z-axis.
Mm-hmm. Yeah, so it's a paraboloid looking like this. And notice you'd get the same shape, same cross section, regardless of which direction you rotated. So whether you're in the pink area or you're in the green area, you're going to get the same shape. It doesn't matter what theta we choose, and theta is again the angle around that z-axis. So very good. Question, Twee, go ahead.
Does that mean theta is constant in this case?
It's not that theta is constant, it's that theta could be anything.
Oh, okay.
Yeah, good question.
You're saying that theta is defined in all.
Exactly, theta is defined in all directions. So one of the interesting things about cylindrical and spherical coordinates is that because they're new systems, we tend to work with pretty simple examples. So those basic shapes that we talked about today, the vertical planes, the